Hey everyone, I am Orko Sinha. I am currently a second year BStat student at the Indian Statistical Institute, Kolkata. I shall be taking your classes in the workshop, and in this session, we shall be discussing a combinatorics problem from IMO 1987. So let's start by stating the problem. So let PNK denote the number of permutations of the set 1, 2, with k fixed points. Okay, and we are asked to prove this. Okay, so let's just go through the question once again. PNK denotes the number of permutations of the set 1 to n with k fixed points. So first question is, what's this fixed point? Okay, we shall explain it at first. So let's begin with the solution. Okay, now solution begins with explaining what a fixed point is. Okay, so consider this permutation. This is the reference like permutation we consider. Okay, because everything is in order, okay, natural order, that is. And consider any other permutation, say like this: 2, 1, 3, 4. If you see here, 3 remains in its original position, 4 remains in its original position. So here the number of fixed points is 2. If you consider this permutation 2, 3, 1, 4, so here just one fixed point. Okay, so after you do the permutation, if an element stays in its natural position, you say that the element is a fixed point, okay, of permutation. So with that in our mind, let's go through this question. This question asks us to prove k times p and k is equals to n factorial. Now this is a combinatorics problem, okay, and we're counting something. So what does this thing count? Let's see term wise first, okay. So k times p and k. What is p and k? All the permutations having k fixed points, and you multiply that by k. So it basically counts the number of fixed points, right? What you do is that when you take this sum, what you're doing is you are just seeing what which permutations have k fixed points, and since they have k fixed points each, you're just multiplying this p and k by k and saying that all those permutations that have k fixed points, okay, you're just taking them and multiplying them by k, and the sum that you get is basically you're counting the number of fixed points in those cases. Okay, pretty trivial, doesn't really require this much explaining, but pretty trivial, right? So how come this comes equals to n factorial? That's the question. Okay, so if we count it like this, what are we doing? We're basically looking at a permutation, seeing how many fixed points there are, keeping that in mind, say k, sorry, not k, say a. Then we go to another permutation and see how many fixed point this has, and let that be b. And we go through every permutation and just add this a, b, etc. And that's what we get in that sum, that is the LHS. Okay. Now, if you think carefully, this is one way of counting this thing. The other way of counting this thing is by looking in this way. You look at a permutation, okay. In this case, what we are doing, we are looking at a permutation and finding the number of fixed points and adding them. And we got, say, a fixed point in this, b fixed points in this, alpha beta fixed points in others, okay, and we just sum them and get the LHS. Now what we are doing is we are not looking that way. You are fixing each element. Say we fix 1 in the first position and look how many permutations have 1 as a fixed point, and we count that. How many will that be? That will be just n minus 1 factorial. We do the same thing with 2. We count how many times 2 came as a fixed point. That will be again n minus 1 factorial, and on and on. There are n such points. So you get what? If you sum these up, n times n minus 1 factorial, which is n factorial, right? What you did this way is exactly the same thing that you did here. Just the approach changed. Okay. Why is that so? So think carefully. What were you doing this in this case? You're going through every permutation, and for every fixed point, you're saying, see, consider this permutation only. This has a fixed points. What were you doing? You're going through this permutation and searching for fixed points. Every time you got a fixed point, you put 1. Put again 1, dot, 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 a times, and you got a. For the second one, what you were doing? You searched fixed points and then put 1 for every time you got a fixed point, and then you get b. Okay. Now what you're doing is you're going through every one of these permutations and looking, rather fixing an element and seeing how many permutations you get having that element as a fixed point. So how are you counting in this case? You are going through every permutation and seeing whether this has 1 as a fixed point. If yes, you put 1. If no, you put 0, and rather you don't even bother about that. Okay. And in that way, add and up and get n minus 1 factorial. So did you observe here what we are doing? Say these two permutations are there, and say in this one is a fixed point, and in this one is not a fixed point. Okay. So what did you do? You went through this permutation, saw that 1 is a fixed point. You said, okay, I'm putting 1 here. You went through this permutation and you did not find 1 as a fixed point. You just don't care about it. Okay. And if you consider here, if you think about it this way, everyone is accounted by some element. Okay. So what were you doing here? Well, we were summing along permutations. Every one you put belong to some fixed point. Okay. Say this one belongs to 1. Here what we are doing? Here also we did the same thing. If you go along the permutation, you just find the fixed points and put a 1 for every one fixed point you get. But you didn't find 1 as a fixed point here. So the fixed points here weren't really accounted by 1. They were accounted by others. And at the end, what we're doing? You're summing all of them up. So when you do that, you get 1 from 1 here. You don't get 1 from any 1 from here. Again, maybe there's some permutation with 1 fixed point. You get 1 from there. And total, you're getting what? Same thing in both these cases. And here we already saw that the sum gives you n factorial. So since we are essentially counting the same thing in 2 ways, the answers must be same. So by that we claim that equals to n factorial. So that's it for today. Meet you in the workshop. Thank you.